Hello and welcome to our project presentation of assignment 5 of our course, Mechanism Sessional ME29002. My name is Adil Mulani, roll number 23MF10024. I am a third year undergrad student of the Department of Mechanical Engineering at IIT Kharagpur.
And I'm Moli Maheshwari, roll number 23MF10025, also a third year undergraduate student in the Department of Mechanical Engineering at IIT Kharagpur. Let me begin by explaining the problem statement we have selected. In Indian Railways, we face a significant challenge. Platform heights vary considerably across different stations, ranging from 760 millimeters to 1200 millimeters from the rail level, while train coach doors are fixed at 1320 millimeters from the rail level. This variation makes it difficult for passengers, especially the elderly people and those with mobility challenges, to board and alight from trains safely. Our objective is to design a ladder mechanism that can adapt to platforms of different heights, providing safety and easy access to railway coaches. The mechanism must be compact when stored, safe, and stable in all the positions. Also, it must be equipped with locking mechanisms for safety.
This problem is highly relevant due to India's railway infrastructure. In India, railway platforms often have varying heights due to differences in infrastructure or historical reasons. Implementing a system like this ladder could be significantly improve accessibility for passengers, especially those with mobility challenges, elderly individuals, or passengers with heavy luggage. Automating the ladder system can enhance safety by reducing the risk of accidents associated with manually deploying or retracting ladders. The addition of safety locks can ensure stability, a crucial factor in high traffic railway stations. Considering India's diverse weather conditions and high passenger load on railways, the ladder system anti-slip technology can offer a robust solution to ensure safety and stability even during monsoons or crowded rush hours.
We are developing a groundbreaking ladder system to facilitate seamless access between train coaches and platforms at varying heights. This innovative design integrates advanced features such as motorized opening and retraction for effortless deployment at the touch of a button. To ensure utmost safety and efficiency, we are implementing a secure locking mechanism for the retracted position, which reduces strain on the motor and guarantees stability. Our aim is to transform the railway experience, prioritizing passenger safety and convenience.
We have used this estimating the distance between platform and train and deciding the dimensions of stairs, selecting the open and closed configuration of stairs, determining the lengths of four-arm mechanism using graphical synthesis, and designing and simulating the mechanism in SolidWorks.
Before synthesizing, we must determine what type of four-bar mechanism we can use. Grashoff's law states that if the shortest link plus longest link is less than the sum of the other two links, then at least one link can rotate fully. Mathematically, it goes like F plus L should be less than P plus Q, where F is the shortest link, L is the longest link, and P and Q are the other two links. If the inequality is reversed, that is, F plus L is greater than P plus Q, then no link can rotate fully. All links only oscillate. This is called a non-Grashof mechanism, commonly used to create rocker-rocker motion. In our design, F plus L is greater than P plus Q, meaning our mechanism does not satisfy Grashof's criteria. Thus, our mechanism is non-Grashof, double rocker, both moving links oscillate, and there is no continuous rotation. This is exactly what we want because the ladder needs finite angular motion only. It must open and close and not rotate endlessly. The mechanism gives stable extreme positions and oscillation is mechanically safe and predictable. On each side, the longest link acts as one ground, the shortest link is the driving link, and the two intermediate links behave as rockers.
In synthesis process, the first thing we did was to sketch the ladder in its two extreme positions. In the open position, the steps are completely horizontal, allowing passengers to climb comfortably. In the closed position, the entire ladder folds vertically and stays stuck safely underneath the train. These two limiting positions form the foundation of our synthesis process. Using these two positions, we perform graphical synthesis to determine where the linkage pivots will be placed. We connected corresponding points from open and closed configurations. Then we constructed perpendicular bisectors of those connecting lines. The intersection of these bisectors gave us the locus of possible ground pivot positions. Since we are using only two positions for synthesis, it doesn't give a single exact point. Instead, it gives us a line of possible solutions. From that line, we selected pivot locations that were practical to build and manufacture. Once we had the locus, we placed the ground pivot based on physical constraints. The ground pivot was fixed 1 centimeter below the train base in a scale drawing. In real dimensions, this correspond about 10 centimeter. The second ground pivot was positioned slightly above the first one. This ensures proper and realistic ground length that can actually be manufactured. These two pivots locations define a fixed link of a 4-bar mechanism. By joining these ground pivots to the points on the moving links, we obtain a complete 4-bar mechanism that satisfies both extreme positions. We then measured all the link lengths in the scale drawing and multiplied them by 10 to reach the real world dimensions suitable for an actual railway ladder. This gives us the correct proportions for the crank, coupler, rocker, and ground links. Finally, we integrated the steps into the mechanism. The coupler link directly supports the first step. The second and third steps are not separate moving parts of the mechanism. Instead, they are rigidly welded to the first step. This approach gives multiple advantages. It reduces moving parts, lowers the chance of mechanical failure or jamming, makes manufacturing much easier, and ensures all steps move together smoothly and consistently. The result is a robust and reliable foldable ladder that is simple to build, perform exactly as required.
Now, let's take a look at the 3D model that we prepared for the railway ladder simulation. What you're seeing right now on the screen is the closed position of the ladder. I'll first walk you through how we build this model in SolidWorks, and then we will see its working at animation. We'll begin with the most important part of the assembly, the rectangular boundary frame. This fixed This frame is a fixed part of the entire system. Both the mechanism and the steps are attached to this boundary. Because of this, the first step is also fixed relative to the frame and it doesn't move independently. It essentially acts as part of the base structure. Now, let's look at the stair elements. This is the first step, and these small parts you see around it are the connecting links. To create the step, we started with a simple rectangular sketch, then we applied an extrude feature to give it thickness. After that, we selected both ends of the step and used the linear pattern tool in SolidWorks. This allowed us to quickly generate 4 additional identical steps. For the boundary frame, we again used a simple rectangular sketch, extruded it, and created the final frame structure. The links were created using the slot feature, which makes it easy to generate the curved ends and holes needed for the revolute joints. Other small connecting parts were made using standard SolidWorks tool like extruded boss and extruded cut. Now, let's move on to the working of the mechanism. When we operate the shaft, the stairs begin to unfold, or we can say that the ladder opens out from its closed position. As you can see in the animation, the ladder opens smoothly, and when we reverse the motion, it folds back neatly. This opening and closing motion is controlled entirely by the shaft and linkage mechanism.
As mentioned earlier, our design uses a double rocker mechanism, which means we have two rocker links and system forms a non-Grashof chain. Non-Grashof chain does not satisfy Grashof criteria, so no link is capable of full rotation. All links oscillate back and forth, and that is exactly what we want for our ladder, which needs only opening and closing motion. The longest link shown here acts as Lmax and it forms one part of the ground. The shortest link, L minimum, and this is the link responsible for driving the motion of the ladder. Both the upper base and lower base rectangular frame act as ground link. Ground link 1 is upper base, ground link 2 is the lower frame. L maximum is largest link connecting these two, and L minimum is smallest driving link. And the remaining two links are the rockers. Two rockers link connect the ground links. On one side, they attach to rectangular frame, and on other side, they attach to a smallest link. You can think of a rocker link as couplers because they transfer motion from the driving link. They help the ladder move inward and outward, and they guide the ladder upward and downward during folding and unfolding.
Finally, there are several improvements that we can add to this mechanism. We can integrate a locking mechanism to fix the ladder in position. The lock can be designed using a simple nut and bolt or pin mechanism. We can also add a motor to automate the motion. And by adjusting the link lengths, we can make the system suitable for different platform heights. That concludes the explanation of the 3D model and mechanism. Thank you for listening.